Welcome back to Incremental, the continuous improvement podcast. This is a shorty episode to fill in for my paternity leave, which is an unknown date. So this will be dropped in the feed when I'm out. I'm Uriel Eisen from Austere Manufacturing and Arda.
And I'm Devin Bedoni of Like and Precision, and we're going to be focusing on kind of a single concept for these little short fill-in episodes. Today we're going to be talking about job shop scheduling problem, traveling salesman problem. I think it's a concept that's sort of like bandied about often, but I know personally I hadn't actually stopped to read about it, and it was intriguing, and there's some kind of curious and interesting ramifications and applications and just how we think about things. So we're going to dive in a little bit. Do you want to lead us off with some stats, Ariel, or should we kind of fill in the groundwork first?
Yeah, so I've been working my way through this book, Factory Physics, by Wallace J. Hopp and Mark L. Spearman. Really awesome read. But just sort of skipped ahead of where I am to dive into this specific issue. And so I really like the way they lay it out in this book. They basically go through some of the computational difficulty of the traveling salesman problem, or in this case, very specifically, the job shop scheduling problem. And essentially, the issue arises out of the behavior of the number of potential routings through a shop with the number of machines you have. And just to put sort of a fine point on that, just a short little reading. Returning to the single machine problem with 3 jobs, we note that 3 factorial, so that's the number of, if you have 3 jobs going through one machine, you have 3 options times 2 options times 1 option. So 3 factorial equals 6. Does not seem very large. However, observe how quickly this function blows up. 4 factorial equals 24. 5 factorial equals 120. 6 factorial equals 720, and so on. As the number of jobs to be sequenced becomes larger, the number of possible sequences becomes truly daunting. For example, 10 factorial equals 3,628,800. 13 factorial becomes 6 billion and a bunch of other numbers. And so you can see how the behavior with very small numbers. And that's the end of the quote. Oh, I guess I should read 25 factorial. So if you have 25 jobs going through one machine, the number of possible options for how to run that job is 15 followed by 3, 6, 9, 12, 15, 18, 21, 24, 0. Well, not zeros, but
Digits.
Digits. So I don't know what number that is, but it's large.
A big one. And I guess backing up slightly, for anyone who has not come across it, apologies if you already have. The traveling salesman problem is just postulating, well, this was a real thing, right, that came up. This is why it became a problem that people studied, was a traveling salesman having to visit many different cities and trying to calculate the shortest distance total traveled that would hit all of the cities, or shortest time. That is so effectively the most efficient route. And that has morphed into a whole field of mathematics at this point, it seems like, from what I was reading. And it applies heavily. What I was reading, it applies really heavily to microchip processing scheduling, which is very interesting that it has so much relevancy across different industries.
Well, interestingly, yeah, totally. And microchips are job shops, right? You have these processing centers. The jobs need to go through them. The customers need to not be delayed too much, or they have some level of delay that they accept.
And there's heavy dependencies. So one stat that I came across that was really interesting was with the job shop scheduling, with the traveling salesman problem specifically, which is essentially one processing center, if that were a person traveling, and many nodes. Or, all right, am I thinking about that correctly?
I think it's you can have the job is the salesman, and the cities they visit are the machines.
Yeah, that could be one way to think about it.
Or
Or
I
it
guess
could
you
be
could flip
they
it.
are the
Yeah,
machine
right.
and the jobs going through them are the cities, whatever. The interesting thing that I noted was that a a relatively simple, so like not a brute force computer program that calculates every single possibility. They have algorithms that simplify it slightly and don't calculate every single possibility because, as Uriel was noting, the numbers get very, very high even for a powerful computer, and it just takes a lot of processing time. So a lot of the approximation computer programs for scheduling get within 1 to 2% of the ideal scenario that you would calculate if you were to actually go through and calculate every single possible solution. What I found intriguing, so that I think, I forget what the term they use for that is, but like basically 1 to 2% compared to ideal. Humans, if the number of nodes, I believe, are 11 or less,
Hmm.
get within 10% of ideal intuitively almost instantaneously. And
That's cool.
apparently many other animals also do this. Like we have some built-in capability.
I mean, we do routing all day, every day. It's like the bread and butter of anything with legs,
It is,
right?
yeah, right,
A little bit.
exactly. Yeah. Um, so that was an interesting stat, and kind of the ramifications that I was thinking about it are that we often get like there's this infinite potential for, or nearly infinite potential for optimization of
Hmm.
routing. But if we sort of take it for granted that we get pretty good kind of right out of the gate, and that it's going to take a ton of work to optimize that last 10%, and it will always be changing. If we kind of lay a groundwork at pretty good and then focus on optimizing all of the waste out of the little steps, that we can probably gain back more than whatever that 10% was at baseline. And I think this is, I'm probably not the first one to have this take, but I think this is why continuous improvement strategies with standardized workflows are so effective, because I think it's possible to really get lost in the weeds trying to optimize and optimize and optimize the routing while never actually making the system more efficient as a baseline.
Yeah, 100%. And I think some of those numbers are exactly like this book basically agrees with all that, which is all of these mathematical numbers, or reasons that the complexity kind of blows up
Yeah.
essentially ignores the fact that we're actually just running a real business. Because two things. One, these assume that you can freeze your factory in time where
Mm,
nothing's set up on any machines, like material constraints aren't really an issue, right? I mean, yes, you can stack all those things in, but the numbers get even crazier the more
they
layers you add
do.
to your optimization problem.
Yeah.
Um,
And in terms of the numbers, just jumping in really quick, like those numbers that you read off were just numbers of jobs through one node. And as soon as you
right.
have dependencies of like in a machine shop, say it runs from this machine to this machine to this machine to this process, those are all layered on top of that initial
Right.
number of variables. So like it balloons to an infinite degree nearly almost immediately in any real scenario.
Yeah, yeah. And so they're basically like you already have stuff running now. So it's not like you're starting from scratch. And so the next one sort of starts to suggest itself, but more than that, I mean, maybe you should have been a third author on this book. Um, but the fact that it's, NP hard is a little bit irrelevant when you're just trying to do work. And like you're saying, really the thing to do is to erode the things that make that routing difficult. So, for example, setup times are a really big factor
Mm,
to try to optimize. Like, oh, well, we have this machine set up and took us 8 hours, right, to get this lathe running this part. So now we kind of want to run all of that family of parts while we're doing that, right? Or we have this machine set up for stainless steel. Let's try to get as many jobs through there as we can that rely on that really high cost of setup.
Yeah,
And so what the
yeah,
Japanese sort of did post World War II is, I think, kind of intuitively attacking the things that make the routing really complicated and hard,
yeah.
rather than bothering with this really goofy math.
Yeah. One one interesting thing I came across was there's a bunch of variants of the job shop problem. I think that specifically apply to chip design and architecture and scheduling
Hmm.
styles, but also like sort of backfeed into real job shops. And one of the variants, well, there's some crazy variants that are just like open, blow off all the doors and like infinite potential of things routing in any direction,
Okay.
which is wild to think about. But then there was one that I came across that was, I think, super applicable as a model, which was called the flow shop scheduling problem. And
Okay.
that is where they effectively sort of designate cells and established flows through a processing, a processor or a shop, or in this case, a theoretical, whatever.
Hmm.
And so you reduce the number of variables by a massive degree once you take the potential sequence out of the equation. So you're
I see.
establishing a fixed sequence in which things flow through, and then all you're dealing with is the sequence that they get lined up in, not the sequence in which they go from machine to machine.
That makes a lot of sense. And then the other interesting thing, which I haven't heard Eliyahu Goldratt speak to specifically, but I wonder if he knew this or if it was just, arrived from a different angle for potentially the same reasons. But the other thing this book does on a similar note is, in the good news of this whole conundrum is that if you focus on your bottleneck, you similarly massively reduce the number of permutations you want to look at.
Mm,
Because, right, we can see how silly the math gets really, really quickly. And so if you're evaluating across every single machine and person in your shop and job, that is, I mean, just practically impossible to bother with. But if you just say, well, screw all that, it's okay if we have some inefficiency there. Let's just look at throughput on our bottleneck. Um, you're really getting back into territory that's actually tackleable and
mm,
useful. Um, and then, another one I think that's interesting as it relates to the Toyota production system is job splitting. So if you have the bigger the blocks are of the things you're trying to push through the system, the
mm.
more each sequence affects everything else potentially catastrophically. If you
Yeah,
consider catastrophic being like missing a due date.
we have
Um,
been dealing with that in a serious way for the last couple months.
Interesting. Yeah. And so if you can split jobs up, notably smaller batch sizes, Kanban is one way of achieving it, but well, not really achieving it, I guess just managing all that.
Yeah,
But if you can do a lot of switching, then suddenly you can relax a lot of deadlines, a lot of the sequencing on specific machines, because every single job in the queue is within bounds on its delivery date almost automatically. It doesn't really, I don't know if it
yeah,
doesn't exactly apply to job shops. I think that's more in production. But
yeah.
even in job shops, if you could make those changeovers so fast that you go like, let's run 10 for this other customer, even though we have to run 200, let's run 10 today to keep them fed, right?
Yeah.
And then switch back to this other job.
The
I don't know.
challenge in job shops, I think it does apply 100%. The challenge in job shops is if you have promised a due date for the large block that requires that it run more or less continuously to achieve that due date.
Mm-hmm.
If you chop it up and slip other things in the middle, then it becomes late.
That makes sense. I feel like people, I've talked to a lot of people about this recently. I feel like people just have weird ideas in their head around due dates and sourcing
Uh-huh.
because they're like, well, we want to order 50 and we need them by this date. And then you're like, okay, so you're going to use 50 on that day? And they're like, no, but we need to ship at least 5 to this one customer. You're like, okay, so you need 5 on this day, and
Yeah.
let's make it 10 to be safe.
Yeah.
And then they're like, yeah, and then the rest we'll use sort of over the next 2 months. You're like, okay, can we relax the due date on the whole batch? But
Yeah,
yes,
I
I
mean,
hear what you're saying.
I totally agree. There are good reasons, right? Like as soon as you
Color
split
matching
an
and
order, what's that?
color
Well, yeah,
matching and anodize.
that is the precise reason this one that we're working on right now
Mm.
is a challenge because like it's multiple, it's like 7 part numbers that all have to get color matched.
Oh,
So
geez.
and they're all large quantities. But like more broadly applicable would be if, it comes down to stupid little things like document tracking. But if you have a single PO that gets now split into 4 shipments, there has to be some good system within the receiving party's company or organization to handle split shipments and not lose them, not get confused when there's supposed to be 50 on the shelf and there's only 5.
Yeah.
All of that stuff. Like that is definitely that's definitely approachable and tackleable, but it's not something maybe a lot of folks are it's silly
Yeah.
because right, like there's huge benefits there,
Mm-hmm.
but people don't seem to see the benefits, so they don't put the work into being able to
Yeah.
handle that, which it would be a small
100%.
amount of work to potentially streamline a lot of headache.
You just sign up with Arda.
Solve all your problems.
That's all you have to do. Yeah, I think right. Okay, so I think like what's interesting about this episode to me is like we've sort of run across this idea in passing many times and kind of talk about it on the podcast in like 5-second increments.
Yeah.
But I think in kind of diving into it a little bit deeper, reading a couple books, or a couple little sections of books on the topic, basically the consensus is that the math gets weird really, really quick. There's no way to prove you're at an optimum, and so the whole exercise is kind of,
Folly.
yeah, it's an intellectual thing, and that in practical terms, what people are already doing tends to be sensible. But I think the other thing I would say that you just brought up is that it is sensible given constraints that are worth shifting. Right. Like moving to smaller batch sizes has a really, really significant impact on how your organization can function. And this is where the math is useful. Like Alexander Slocum, who wrote this book, Precision Machine Design, his whole philosophy is basically that the math is essential to know so that you gain intuition that are like globally true. Right. Like we talked about like rotational inertia or like the bending force on beams. Like if you know the math, you just know when you're in line with how with what the math means.
Or when you're out of bounds, basically.
Yeah, and you know that it's like a goofy pursuit to increase to increase the stiffness of something when weight is a consideration. I don't know, like the square cubed law with airplane design, and like the spruce goose is a classic story of someone pursuing something that math could have told him really early on was sort of a goofy.
Can you elucidate for people who don't know that one?
And I could be mistaken. I think it's in the Freedom's Forge. Great book, recommend it. Building the spruce goose square cubed law, basically as your area increases, your lift as your area, the area of the wing dictates, and forgive me anyone who knows more about this, but basically your lift increases.
I can read it if you want.
With the square, and then the mass increases with the cube of your wingspan or something like that.
Surface area and volume as an object size increases. Volume increases faster than surface area, meaning that as an object gets bigger, its weight or mass increases more rapidly than its ability to support that weight, assuming it uses surface area to support its weight.
Yeah. So basically what they were pursuing was mathematically challenging given the materials they had.
Yeah.
spruce. Well, it wasn't spruce, um, but I think something that's really interesting that just popped into my head is that given how bad, given how impractical it is with this math, to run optimizations on your actual live sequencing,
Yeah.
right, day to day, there's really no gains to be had from a practical perspective for me of trying to chase optimization there. Where I can chase optimization is in the system that whole thing flows through to relax some of those parameters, which is basically lean, right? Like setup times, wasted motion, like all the wastes, just driving
Yeah.
those down. It doesn't matter what jobs I get in the door. Those are all going to be useful. Whereas otherwise, if I'm just trying to make like a better algorithm or something, I mean, most people aren't pursuing better algorithms. They're just sitting down and going like, oh, let's think
Right.
hard today because we
Yeah.
have a lot
Most
to push
people are
through.
just being frustrated and shuffling, trying to make it better.
But
No, yeah.
with inputs that are variable, with inputs that every single day are going to change a little, and so you're not net increasing the performance of your organization. You might get a really good guess today and really fit your jobs into the schedule and machines you have allotted really nicely,
Yeah.
but tomorrow that all that work is totally out the window.
Yeah. 100%.
All right. I also cracked this book open, which is the Shingo Production Management System,
Ooh.
which I haven't read Shujiro Shingo in a little bit, and
Uh-huh.
just awesome. So dramatic reductions in lead time, 3 factors. So one is production cycles can be reduced 80% by eliminating process delays and using full work systems to synchronize processes, meaning
That's
when,
a heavy sentence right there.
yeah,
Let's
basically
break that
when
down.
a job, if a job needs to flow through uh, five work centers sequentially, you can reduce 80%, typically 80% of lead times by just not having any waiting from the time one work center is done to the time it goes into the next work center.
Mm,
And then 2, they can be cut 90% by eliminating lot delays. So a lot delay is if you're processing 10, when you're processing the first one, the other 9 are waiting.
yep.
And then when you're done with that first one and you start on the second one, now that first one, even though it's finished, is still waiting because you're passing it to the next machine in a lot of 10.
So basically same principle, but applied to the lot instead of between
And
work centers in a lot.
yeah. And then 3, they can be reduced another 90% by cutting processing lots to 1/10 of their current size. Um, I don't really understand what the difference between 2 and 3 are, frankly, but regardless, I'm sure if I read this.
Well, wasn't the second one saying as long as the lot proceeds to its next, point on its travels immediately versus the lot as a whole delaying? I think what he's saying was if you don't have delays between work centers for a single part, you reduce by 80%. Then I think what he was saying after that was if you are producing in lots, if you don't have delays between work centers or between, processes of the entire lot, you can reduce by an additional 90%.
I'm not sure exactly. Either
What
way.
was the last one again?
The last one is they can be reduced another 90% by cutting processing lots to 1/10 of their current size.
Oh, so I think that's just like reducing batch size by a factor of 10.
And what's number 2? They can be cut 90% by eliminating lot delays.
So
Lot
I think what
delays
he's
in production
saying,
cycles. Now let's
yeah,
look at how the combination. Well, anyway, we don't need to do this live.
I think he's saying because lots often do sit. Like if you are producing in lots, they often do sit between a work center or between processes.
Wouldn't that be process delays? I don't know.
But if you're doing it by a lot, maybe he's calling it a lot delay.
Maybe we'll tackle this a little deeper. The point was, the reason I brought this up is Well, firstly, job splitting is very powerful. But I think one of the things that I was thinking about is like a lot of this optimization is sort of, as I've seen it and heard it talked about and seen it, is really focused on utilization of work centers rather than on the main thing, which is does the customer get what they want, right?
Mm,
Which is kind of interesting. But like here, imagine how much you could stand out if you could. So they gave a real example here of cutting. So in applying those ideas, um, a company in Colorado cut production lead times from 4 weeks to 2 hours, shortened a 1.5 hour setup changeover to a 2 minute changeover, abandoned anticipatory production and began producing only to firm orders, eliminated all finished goods, eliminating all transportation and inventory between processes by adopting a process sequence based layout. Point is, the people just want trucks in this case, right? And so the fact that your welder is idle now 50% more, people get wrapped up in trying to optimize your welding station or your
mm,
CNC, and it's like, who cares about that? I mean, I totally getting wrapped up in that because they're really
sure.
expensive when you're starting out anyway.
Right.
But more and more, I think I think it's sort of optimizing completely the wrong thing rather than just like, hey, is there any way we could get this order done 10 times faster,
Yeah.
right? And just shipped? And then could we charge twice as much or could we, right? Like what effect would that have on the business?
Or even not charge twice as much. It's like if your throughput goes through the roof, you can probably charge less and still make more money.
Yeah, so these guys so Grenville Phillips is the company, cut labor costs by 60%, plant floor space by 40%. The company installed new equipment in the newly opened space and used the 60% labor surplus to manufacture new products. So yeah, I mean, there's just like huge gains just inherently. Um,
Yeah.
so anyway, the conversation of like routing optimization, I think is just like maybe worrying about something that we can't optimize to the
Uh-huh.
fullest, and everyone's probably doing a decent job of right now.
Yeah.
And so really we should just ignore all that and move to standardization of, like you were saying, of sequencing so that we can work on work on improving how everything happens rather than how this set of constraints are going to happen.
Yeah.
Um,
I think it gets focused on because it's like clear and present,
yeah,
right?
yeah,
And feels like a lever you can pull. But the reality is like the lever's kind of stuck. You can't really pull it very much.
yeah. So in terms of compute times, this is kind of interesting. They have a chart here. If you have, let's see here, wrong page. If you have 5 jobs, your compute time will be 0.12 milliseconds. This is assuming a certain performance. And then they
Sure.
compare that to a computer of 1,000 times faster. So 5 jobs would be 0.12 microseconds instead of milliseconds. So let's go with the faster computer.
Uh-huh.
I'll just skip around 10. You're going to be at 3.63 millisecond compute time for all the combinations. 15, you're at 21.79 minutes to compute all the combinations.
Whoa.
20, you're at 70.147 years to compute all the combinations.
Whoa.
Anyway, yeah, I think like, yeah, I don't know. I think exponential growth before digging into this felt really awesome to me. And
We
now I'm
could
like,
make the most niche meme with with those numbers, with the guy with his head exploding at the
oh
end.
yeah, it's pretty niche. Anyway, so yeah,
It
but I
would
did
not
like
be a meme.
how they kind
No
of
one
broke
would.
it down. They're like, here's the math vaguely, here's why it's hard, and here's also sort of why it's irrelevant and how to kind of just set it aside and work on the things that are actually actionable.
Yeah. Irrelevant unless you are designing microchips, possibly. At which point
Yes,
there's some relevance.
I think there's a lot of relevance because for a bunch of reasons. Like, uh, let's see. I wonder how many jobs you're going to process in the life of Lichen.
Oh, yeah, I don't know. I
It's probably
mean,
less than like a second of a microchip.
yeah, yeah,
So
exactly.
your total gains for optimizing sequencing probably feel a little lower. Um,
A little bit.
I don't know. Anyway,
Multiplied by the number of microchips in the world. Yeah.
and it feels like they're a lot more standard. Yeah, right. Right. Yeah. Like more microchips are produced per second than leaves in the world or something like that.
Whoa.
Uh
What?
yeah, that's out of The Perfectionists, the
Yeah.
book.
Okay, yeah, I remember that.
Um
That's a great.
that's just mind blowing. Anyway,
Also, there's
this is
things you can
allegedly a shorty.
yeah, there's things you can do in computer chip processing that are like harder, right? Like
Your
it's very
setup
easy.
times, yeah,
Well,
are
setup times, and then
different.
also like when we're talking about like uh, chopping up jobs into smaller bits, like
Mm,
that is very, very
smaller bits. I see what you
straightforward
did there.
for a piece of math, I think, where right, you like com compute it to this
Possibly.
point, then set it aside, then that which is the thing that happens, I believe, where they're like
Right.
bits of not bits like technical bits, but like pieces of of jobs get a hierarchy, and they're calculated for a certain duration of time that's preset, after which if they're not done they get kicked back to the back of the hierarchy, and stuff with higher priority gets
Hmm.
moved through, and then once they come through then it get finished. That theoretically could be possible in processing real goods, like
I,
definitely, but it's a little bit more complicated. Like
yeah,
the ramifications are higher, I think.
I would imagine that in a purely theoretical sense, actually, microprocessors are exactly the same problem. Because you do have setup times and putting stuff in and getting stuff out of memory. Of my
Yeah,
understanding. I don't know. I know nothing about this virtually, so
for
maybe I'll
sure.
stop talking about it. But I bet that reading more about that specific methodology would be useful. It also strikes
Hmm.
me that like Toyota just skips all this by making the packet sizes small enough
Yeah,
that every processor can just process the packets in their order, and then you have 20% capacity flex,
yeah,
right? And then you can also overclock that microprocessor by having your flex labor come in for additional shifts. And
sure.
so suddenly it's like we don't need to bother with any of this complex mathematically uphill battle stuff.
Yeah.
We can just reduce lead times by 500% by doing other things. um,
Cool.
anyway,
Well, yeah, our shorty got longy.
yep.
That's probably a good place to wrap it. You can find me on Instagram at lichen_MFG, on the web, likenprecision.com. Please reach out. You can find the pod at Incremental CI, and definitely reach out to us there.
Yep. You can find me at austere_manufacturing on Instagram and austeremfg.com on the internet. Post a lot of improvements, especially over the last week, over on the Instagram. And Arda is arda.cards on Instagram and on the internet. We just put up a new website with a new video. We'd love feedback. And we have a Patreon, so check out the Patreon, and we'll be back next week.
Adios.